désolé pour le retard.
Sorry.
Et donc, voilà, nous avons Yuan Miao, qui est en visite à l'IPhT pour une semaine, et qui a la gentillesse de faire un détour pour venir nous voir aujourd'hui. So, you talk about classical integrity.
Yeah. Okay. Yeah. Good afternoon, and thank you all for coming here. First of all, I'd like to thank Vincent for inviting me to give this talk about our recent work on how to study the semi-classical limit of quantum XXZ spin chain, and more importantly, how to obtain some quantum properties from studying the classical limit of a quantum spin chain. And also, I work with my collaborators Sasha Gamayun, Ine Ilevsky, and my supervisor Jean-Sébastien Coe. And I'm at University of Amsterdam. So so hopefully by the end of the talk you would understand what this diagram is, which looks quite nice, but right now it doesn't make any sense, but I'll try to explain. So let's start with some motivations why we are interested in studying this semi-classical limit of XXZ chain. So what motivates us to look at this problem is a well-known problem in the quantum out of equilibrium physics, which is the domain wall quench in the XXZ chain. So basically the setup would be very simple. So you put all spin down on the left of the chain and all spin up on the right of the chain. And it's ferromagnetic chain. You join them together times 0. And you would like to study the time evolution of this spin chain. It looks very naive, very simple, but however, you immediately run into problems. For instance, you cannot use the familiar linear response theory for this model, and it's kind of a quantum quench, and more importantly, it's an inhomogeneous quench. And the model I study here, as I showed you, it's a ferromagnetic chain. That's why there's a minus sign there, and it's XXZ, so there's some anisotropy delta. When delta is 1, it's isotropic, so it's the famous Heisenberg model. And actually this model has been studied ages ago. So for instance, let's say decades ago, by some people doing numerics. For instance, first paper that I found is by Gobert and collaborators, and what they study is they just put this initial state and time evolve it with DMRG. And what they found is actually quite surprising. There are 3 different regimes of this model, the out of equilibrium physics. So first is if you put it into the gapless regime, and you will see, for instance, so these contour lines are just spin with some fixed value, let's say 0.1 and 0.2. And you see that, okay, there's some ballistic transport of the spin that leaves after the long time limit. And here at the asymptotic point, it's not so visible in this diagram, but I will show you another one, that here instead of being like a ballistic, it starts to have some curvature there, so it looks like diffusion but a bit faster. So it remains a long history of some mystery about that, but which I'll just mention in the next slide. And then for the gapped regime, you see that the contour line is basically confined around the region, which means the domain wall is kind of frozen. And also there are some other modes which looks like they travel with some velocity, but this mode doesn't contribute much to the spin transport. So it contributes to of order 1 contribution. So at the long time limit, these modes are not very important. And most recently, we studied this model, and together with many of you might know here, with Gregoire and Vincent here, study this model, and we realized that actually you can, just by studying the classical model, the classical corresponding model of the quantum spin chain, you get more or less the same out of equilibrium behavior. For instance, at the gapless regime, which in the classical language people call it easy plane regime, you will find also the ballistic transport, and more importantly, the quantum case was solved analytically by generalized hydrodynamics by Korura, De Luca, and Vitti. And then for the asymptotic case, you can no longer use hydrodynamic GHD theory there, and you need to study a bit harder. For instance, for us in our case, we study classical model using inverse scattering method, and we conjecture that it's probably there's diffusion but a bit faster with a log correction. But today I will not focus on this. But today I will focus on this regime, which is the gapped easy access regime in the classical case. And in the classical case, you will find out that there exists some solitone there, which explains more or less why the domain wall is frozen, because solitone is non-dispersive. And meanwhile, you could also find some radiation, which is the mode that I showed you the last slides, that also travel very fast, but it has very little contribution to the spin transport. And the main point here, we want to understand why on Earth the quantum case could also have like similar behavior as the classical one. And more importantly, for instance, I show here, you see they are not really static solitone. They are like a solitone with a breather on top of it. And this hasn't been absorbed in quantum. So we also would like to understand what is going on there. Yes, and then so today I will start with the quantum spin half Heisenberg chain, and hopefully many of you might be familiar with the Bethe ansatz. So I'll start with Bethe ansatz, and I'll show that if you take the semi-classical limit of the Bethe ansatz, you will get to this asymptotic Bethe ansatz, which is equivalent to a Riemann-Hilbert problem. And meanwhile, this is not the only way to take the classical limit of the model. You can do, for instance, you can start with the Hamiltonian, and then you can try to find what is the classical Hamiltonian, or you can start with the transform matrix for the XXZ chain and try to find what is the classical transform matrix, which give you the auxiliary linear problem for the same model, which is the classical Landau-Lifshitz model. And more importantly, we realize that the asymptotic Bethe ansatz gives actually the finite gap integration for this classical model. So I start with the third approach, and then in the middle I will just show you the other two also works. And the most let's say surprising part of my talk would be actually by studying this asymptotic Bethe ansatz, you can actually calculate the overlap for a semi-classical state of the XXZ spin chain. So this is purely quantum object, so the overlap of quantum states. And I'll try to convince you that this works. Okay, so we start with XXZ chain. So the Hamiltonian, as I showed you as before, so it has just nearest neighbor interaction with some anisotropy term. And there exists the solution which solved first by Hans Bethe in the 30s, and this is called the Bethe equation. And maybe some of you, are you all familiar with Bethe ansatz, or kind of? Okay, if not, I can explain. But yeah, so the idea is just to see that you start with a ferromagnetic state, let's say this the vacuum, and then you can add excitations which characterized by some number called rapidity. So rapidity is a way to encode the physical momentum, for instance. And here I write for the model with the anisotropy, which this eta is proportional to cosine or inverse cosh of the anisotropy parameter here. So when at isotropic, so basically the trigonometric function will become rational function. And here I write the exponential of some object p here. So this p, I will call it a quasi-momentum, and it's the generating function for all the local conserved charges of this model. I consider, so people usually consider this model in a limit. It's called thermodynamic limit. Namely, you consider for n total spins with m spin downs. Meanwhile, the number of down spins is of order infinity. But however, the ratio between the down spin and the total spin of order 1. But in this case, you usually consider the number of excitations also goes to infinity. So there are many excitations, and usually in this case, you can characterize your solution by, for instance, using this so-called strain hypothesis, which basically means if you have a bound state of spin downs, they will have the same spin strain center at some real number here, and however the distance between each spin in the rapidity space would be some fixed number, fixed imaginary number proportional to the anisotropy. And basically, this only works when the bound state size is very small. It's of order 1. And then the ratio between the total number of spins goes to 0 when your system size goes to infinity. But that's not the limit that we are interested in. So we're interested in, so we keep the first 3 requirements. Meanwhile, we see that the number of excitations is actually of order 1. So there are only few of these excitations, which means the bound state is actually pretty large. So I have lots of downspins. They form a huge bound state. And that's the limit that I'm considering. But in the end, you will see that this is actually related to the domain wall quench that I introduced at the beginning. But at the moment, it's probably...
Oh, wait a minute. So
yeah.
You said you keep the first 3
yes.
conditions, and infinity, and the bottom one.
That's right.
And
Yeah.
over n, if I understand it correctly, probably the number of excitations.
No. I mean, the number of excitations, what I mean is, so basically the number of bound states are there. So of course there are a number of downspins, but they might form one bound state. I call just one excitation. Yeah, so if you have, let's say, I don't know, 10 spins, they form a bound state. It's not 10 excitations, I call it one excitation. Yeah? Okay. So let's take a look what happens when the number of excitations are just of order 1. And apparently in this limit, you will see that the string hypothesis will no longer hold. So you cannot use string hypothesis. This the repetitive they no longer live on the imaginary. Let's say they are centered at the real number, and they all have different imaginary parts. However, they will have some kind of a curvature there, and this we call it a giant string. So it's a giant bound state that looks like a string. So, but it has nothing to do with string theory here. However, in order to study these objects, it's more convenient to take some semi-classical limit because of finite and sort of big delta, so capitalized delta, is not so nice to study these objects. So what we are considering is actually a point that, so A is the lattice spacing. So here the small delta is basically proportional to large delta minus 1 over the lattice spacing squared, and this quantity is of order 1, which basically means my anisotropy is very close to 1. And more specifically, I would like to consider it's larger than 1, but very close. And this is the limit I consider. And then you can do the expansion on the this parameter eta, which is basically arc cosh of the big anisotropy here. And in this limit, you can rewrite your Bethe equation. So basically, okay, first I take the logarithm of it, and then you rewrite it, expand on in the order of 1 over n. So basically, small a is of order 1 over n. And in this case, you actually can rewrite your Bethe equation, which is the product of lots of terms, in terms of some new equation, which is basically some function here plus some 2 pi, which given by taking the logarithm, and then some sum of some other term, which depends on the difference between them.
So what is the main difference between that equation with the one?
Yeah, so the difference is that I take the semi-classical limit, so that I omitted lots of higher order terms in terms of 1 over n. Yeah. So if you want, yeah, please.
You cannot replace the sum by an integral.
I will get to that in the next slide, I think. Yes. So yeah, so this actually the asymptotic case was first studied by Sutherland in '93, and then recently by Kostov and the collaborators. And more importantly, this you can historically it's called asymptotic dynamics. So it's kind of a semi-classical limit of Bethe equations. Yeah. And then actually, what we would like to do is to see, as Vincent mentioned, I would like to replace this sum by some integral. So that's something I would like to deal with. And the point is, so since there's a 1 over n, so you can in principle write some density function, and this density function basically count how many Bethe roots that you can go through in the complex plane. And then you can rewrite it in the, so the point is you write 1 over n and replace the sum by some density function rho here. However, there's a constraint here is k not equal g, so you need to write it as only the principal value. So you need to take out the divergence. And if you're familiar with this kind of complex analysis and things, so it's a very well-known problem. So this is called Riemann-Hilbert problem. And the idea is to say that, okay, I use a new parameterization of my rapidities, which will become very clear why I use this, but then it becomes some analytic function on complex plane mu, plus some jump here when you cross the cut, and then some the principal value that encodes some physical quantity, which is the density of the Bethe roots. So you can imagine the Bethe roots, they get very close to each other, so they condense. So this is the kind of the density of the condensation of the Bethe roots in the complex plane. And this is the equation that you would like to solve. And the nice thing about this is you can actually rewrite this part as, for instance, you write the whole integral, including the delta function there, and then you can subtract this mu here, and then because you can add by the two value along the cut, so that you can get rid of the the delta function part. You're only left with this principal value, and then this in the end it condenses to solving this equation. But however, here I'm abusing a little bit of knowledge here. I call it quasi-momentum. So at the moment it's not so clear why this is the quasi-momentum of whatever model it is. But it turns out that it is related to the finite gap integration of the classical Landau-Lifshitz model. So this P is actually the quasi-momentum for the Landau-Lifshitz model.
What is the contour CJ?
Contour CG, yes, good question. So CG is, so in principle when you solve the Bethe equation, right, so you will get discrete value of the Bethe roots. And when they condense, you see that there's a contour that from the two ending points that connect them, and this contour is not specified immediately from this formalism, but it will. I will come back to that at the end of my talk, and to convince you that actually you can determine the contour which gives you the real physical location of the Bethe roots. So at the moment, okay, it's some contour that a priori, let's say I know. So I write down the contour here. Yeah.
It's a path, right? Not a contour.
It's a cut. It's a branch. You can think of it as branch cut, because this function P will jump when it crosses to the branch cut. So it's some path of the branch cut. That's why it's used. Yeah.
What's on the picture exactly? 2 copies?
Yeah. So this maybe let me explain it a bit. Yeah. I just want to show you something. So it's something here, and then this parameter will become important later. But I'll also explain why there are these cycles. These are really cycles, right? So I'll explain what are those cycles. Yeah. So now I take a bit detour. So I want to say that I want to show you that why this is actually related to this problem, which is at the moment not clear at all. So it's just some mathematical fact that you can write the asymptotic Bethe ansatz as some Riemann-Hilbert problem, but it's not so clear at the moment what it is. So for instance, you can map. Now I try to do the alternative path, which means I want to map my quantum Hamiltonian into the classical one. So how to do that? So first I start with my quantum Hamiltonian, and I would like to write it in terms of my path integral formalism. So you can write it as some expectorelli of some coherent state, which you can think with it lives on a S2 on a sphere. So they are like a vector live on a sphere. They are spin coherent state, and then you get this action. And here you say, okay, so this is the normal term, and then you have some West-Tumino term, which actually not so important in my story. And then I take one limit, which is the continuous limit. Namely, I want to take the lattice spacing goes to 0, meanwhile the number of sides goes to infinity. And there, this part will, instead of ni minus nj, it will become some derivative in x. Yes, and then here this s is, so this is kind of like you take the quantum model and then you write down the classical action and you omit all the quantum fluctuations around the saddle point. So this is the classical limit that I'm considering. And there you would get, for instance, this a sigma model. It looks like a sigma model because of this term, and it lives on a S2, and it's a classical field. Yeah, so this model is being studied many decades ago by Landau and Lifshitz, and this is kind of the continuous limit of my Heisenberg model. But you might also say, okay, we can also take classical limit by taking the spin to go to like large S limit, which means the spin goes very large. And indeed you can do that, but then it modifies a little bit of the interaction term. It's no longer just next nearest neighbor, but it has some log term. But this I will not discuss in this talk. So this is also alternative way to do that, which also been shown that lots of physics are very similar. But I'm more interested in the continuous limit, which means my my lattice spacing goes to 0. And here you immediately see that my small delta parameter will become very useful here because it's exactly this parameter in front of the field theory.
I mean, it's weird that we take the double limit, but the n disappears, that the I survives.
Yeah, so yeah, in a sense, yes. So I mean, I take the limit both, and then I keep this big delta to be of order a squared, so that this quantity is of order 1. Yeah, this is the limit I like. Yeah, so and you can also do this for transform matrix. So if you start with let's say quantum xz transform matrix with the auxiliary spin of spin half, you would get this Lux operator. And here you see that, okay, it's related to this anisotropy eta, and also my rapidity theta here in my original quantum Bethe equation. And then I take the limit when eta goes to 0 with the 1 over n. And there I can rewrite my Lux operator in terms of just identity plus some small quantity, and then higher order with eta squared, which I just neglect. And in this case, if you take the transform matrix, which means you take the product of your Lux operator and you trace out the auxiliary space, you immediately find out that, and okay, you also need to kind of rescale with some large quantity, but this is just for normalization. And it becomes some, so because it's a product of 1 plus something, and it will become just the exponential of some integral of some matrix U. And this matrix happens to look like that. And this actually, if you're familiar with the classical integrability, this is very familiar to you because this is just one of the zero curvature condition for the connection of the Landau-Lifshitz model. So and the meaning basically of zero curvature is just to say that if you want to evolve, this is classical. So you evolve a classical spin from x at time 0 to y at time t. You can do whatever way you like because the connection is has zero curvature. So you can evolve. This is basically evolve with u and then evolve with v, or it's equivalently to do some other path. And this already kind of hint us to that even in the level of the transform matrix, the classical limit of this model is the same as the Landau-Lifshitz model I showed you one slide before. And now I go back to the classical model. Now I focus on the classical model. And the classical Landau-Lifshitz magnet has equation motion, which looks like here. So when it's isotropic, basically my little delta goes to 0, so there's no this term, and there's only the this derivative x squared with spin. And this is the transform matrix that I've written down. And basically the eigenvalue, so we all know that the eigenvalue of the transform matrix would encode all the local conserved charges. And indeed it is the case, so you write down, for instance, the transform matrix, and then you can take the trace of the transform matrix. It becomes some function of the quantum momentum, which which you can expand on your spectral parameter mu, and this gives you all the local conserved charges. So so this Q1 is the momentum, Q2 is the energy, and so on and so forth. But what I mean by finite gap here, so there's no gap, right? And the meaning of here is more or less from the mathematical point of view. So I consider periodic boundary condition, and in this case, you can map this problem into some problem in the Riemann surface, and since the Riemann surface, you can also view it as some some torus with a different number of genus, and the number of genus is called the number of gaps in the math literature. But here you don't need to be bothered so much. So I'll show you basically one solution which is just have one cut, it's kind of a zeros genus in this case, or two cut, which is a bit non-trivial here.
But you want to keep the size of the chain finite.
So the number, okay, so this is a double limit. So I would like to I would like to set my total number of spin goes to infinity, and my lattice spacing A goes to 0. Meanwhile, A times n, which is the size of the classical problem, which I call small l, is of order 1. So this is a kind of a, yeah.
Is that the same problem we studied?
Yes. Okay, so that, yeah, so okay, so the thing is, because I want to study the limit of my Bethe equation, which lives on the periodic boundary condition. Or I mean, you can put a twist, but I don't want to. So if you put a periodic boundary condition, I need to study the periodic boundary condition solution of my classical model, and then try to match them. That's my idea here. And then the very surprising thing happens is that, so this is purely classical, and you realize that the quasi-momentum, since you can expand on the spectral parameter to get the conserved charges, it only depends on the value of branch point. So I showed you the previous slides. There are some branch cut, but however, the conserved charges only depends on the location of the branch points. And however, it's also true in the quantum case, which basically means if you solve Bethe equation, you can have the two branch point, and then there are lots of Bethe roots live in between. But however, the conserved charge is only determined by the two complex conjugated branch points, or the Bethe roots that are like the ending points of the Bethe roots. But this I hopefully will show you again in the later part of my talk. Yes. Okay, so now I will explain to this diagram, which is a bit complicated, but so there are some analytic properties of this object because they live in a Riemann surface. And the point is, the derivative of the quasi-momentum is actually a very fundamental object of the Riemann surface called the spectral curve. And this dp has, for instance, some second-order pole at plus and at infinity on both sheets. And it also has some properties such as the A cycle vanishes. So this AB cycle, you can think of this if you are on a torus. They are basically, you can define two fundamental cycles, and they give different values. For instance, if you integrate along along the cut here, which actually is the same as along the other one if you only have two of them, and this gives you 0. And if you integrate along B cycle, which means you first start with one cut and then go here and then tunnel through the cut to the other sheet, and then you go back, and this gives you some 2 pi integers. Okay, the 2 pi is some normalization, but I choose this for the
Ni and nj, are they get quantum numbers?
yeah. So the Ni nj is exactly the quantum number that appears before in the asymptotic Bethe ansatz. But so far I still haven't showed you that this solves the equation. But okay. Sorry.
Why A cycle should be 0?
Yeah. Well, it's kind of a
Condition.
yeah. So in a sense, you need to yeah. I would say you can prove that this object that satisfies the equation before have this property that A cycle vanishes.
You describe the model. So this is a condition which you particular
Yeah. Yeah, it's yes.
If I will relax the condition for a cycle different from zero,
It will not solve the equation.
it
Yeah.
will solve the equation.
Yes.
It will solve the equation. It will give you some different states which don't belong to the Hilbert space of your model. There's complexified version of this model which has to be.
I'm not sure if it. Yeah. Okay. So in a sense, of course, you can write let's say the linear superposition of, you know.
No. So imagine I don't know which model you're talking about.
Okay, that's very fine. That's fine.
I have one expression for the spider moment in terms of integrable motion.
Right.
So these two conditions will give me quantized spectrum of integrable motion.
Yes.
Then if I go back to the original model, I know the spectrum of my integrals of motion. First of all, it depends on the space of function which you're looking for the eigenstates.
Yes.
So therefore, a priori, I could put a cycle to any value, and for this any value, I will get some set of numbers which probably will correspond to another model, not your model, but another model. But the both model will have the same equation of motion. The difference between those models will appear at the level of the space.
Yeah. There. Okay. Yeah. Okay. So it. Yeah. It might be true, but so one point. Yeah.
This means I think that in the infinity,
Yes.
when repeat it very well,
Yeah.
momentum is has no cuts. It's analytic. Yes.
At infinity.
Integral of dp.
Integral of dp at infinity is an yes.
And this is so in the XMP model.
Yeah.
Asymptotic is given by just the charge, the total length of the charge.
Mm-hmm. Yes. I no. No. Okay. So.
Because complexified version of the model. So you're talking about model when your spin lives on the sphere.
Yeah. That's true.
And imagine I want to solve the model on which spin lives with the sphere, but takes complex value.
Yeah. I will comment on that. So in the sense that if you just solve this problem, even okay, I'm not yeah, okay. So if you solve this problem that I showed before, this Riemann-Hilbert problem, you still need to identify whether your solution is physical or not. Physical, by physical I mean it lives on a, as you said, it lives on a S2 sphere and it's always real value. You don't want the imaginary spin field, for instance. It's not physical. And this gives you some additional constraint. For instance, you would like this branch cut, the branch point to be complex conjugate. If you relax that, you will still get a solution, but it will not be physical. Yeah. So that's true. That's true. Yes.
How is to be so?
Mm.
So your rho is the discontinuity of P on some cut, which we
Yes.
Is A the contour that surrounds this cut, or which
Yeah. A goes around. So let me draw it again. Maybe it's not so visible from there. So what I mean here, you have the complex plane. So this is the real of mu, imaginary of mu, and I have some cut which is a complex conjugate. Maybe I have many of them, and then my A cycle is here. So this I call it A.
So it's maybe normal that you integral over A dp because you're coming back to the same point. So you integrate, it's P of the point minus P of the same point. So integral of dp has to be 0 then. On such a contour.
Yes, because it doesn't never jump. It never jumps. Yes. Yes, indeed it's 0. Yes. That's true. Yeah, because P is analytic along the whole contour. And yeah, so maybe I think A cycle should vanish. So
Once again, what I was saying
yeah.
that you didn't proposing your quantum model.
Yes.
So you start solving your problem without specifying what the conditional physical state of physical conditions in Hilbert space on your space. Because
Yeah.
certain condition, as you just said, we
Yeah.
should select among solutions those which call physical, which call unphysical.
Mm-hmm.
Right? So
Yeah, I
the
agree.
The quantum system is corresponds to the fact that if you solve some particular solution to a Benazir's equation,
Yes.
you have to be sure the state you identified belongs to your Hilbert space.
That's true.
If you go to classical limit, you're losing this part of the information.
That's true. Yes.
Therefore, someone will be looking back.
Yeah.
So you have to impose additional condition which select.
Right. I will explain that as well. Yeah. So at the end of a few slides later. But yeah. Yeah. Okay. And then the B cycle, if you want, is you from this cut, you go to this cut, and then you go to the other sheet. So you integrate back. So this is on the other sheet. So and then so in a sense, if you write it out, so it's just it's basically just p x plus I epsilon plus p minus I epsilon, something like this. So yeah, so this is actually trivially satisfied because yeah. So maybe I can show you later. It's better. And then so the number of B cycles actually is basically number of cut minus 1. But however, you can define some additional B cycle, which is not necessary, but it's yeah. So if someone's interested, I would like to discuss maybe after my talk because it's not necessary for my main part of my presentation. And there's a typo here, so there's a plus here, if you want, because yeah. Sorry that I made a typo here. And the point is, then you can define some density function. So the density function, as Vincent commented, is just the jump. So, and the reason why this is the case, because if you look at before, it you can write at the principal value and then the jump, and then you can subtract the principal value, and then you get the rho. Yeah, because it gives some delta function there. And then this density, actually, if you integrate along your cut, you will get something called filling fraction. And this I will maybe show you in the next slide or the next one. Okay, let's start with some physics. So some examples. So first example you can think of is this classical solution. So you just say, okay, I put two branch points, they are complex conjugate, and I just just have some cut here. And why this cut is this or not this, it will become clear after a few slides. And then the point is, here is only one giant Bethe strings in the quantum case, if you want. And you can immediately solve the equation just analytically, and then you can get your dp. And more importantly, you can get your spin field. So the spin field is actually very nice. So you see, Sz is a constant, while Sx and S minus, they are like sine and cosine, so they alternate. And physically, you can think of it as some spin wave. So you fix the same Sz, and Sx and S minus, they like spin precession, they just move accordingly. And then you can, for instance, calculate the filling fraction, which means how many down spins are there. So so this, or how many not excitation, we don't have one excitation, but how many part of the m over n is. So this is the filling fraction. And then you can integrate out this object, which this is correct here. And then you will realize that, okay, in the end you would get the correct value. So because the integral of Sz is basically the total of, so the size, so if you have one downspin, the 1 minus the integral of Sz will give you 2. Yes, so you, okay, so yeah, so in a sense that if you integrate Sz, you would get 1 minus, just 1 sec. Yeah, I think, okay, just imagine if you have all spin up. Then if you turn one spin down, you basically, your delta Sz is just 2 times half, if you want. And this is exactly here. And then you realize that, okay, it's exactly the physical one. That's, it counts how many down spins are there. And this is kind of a trivial example. So this works for, so if you're interested in the asymptotic limit, which is studied by Kostov and collaborators, you just set this small delta to 0 and everything works. But then I'll consider something non-trivial, which doesn't exist in the asymptotic limit, which we call it a baryon. So a baryon means you have two giant Bethe strings, but they have the same center, and they all center at 0. And this could exist because you have a specific, you have a special a parameter which is delta. and then they kind of split. They have I square root of delta and a minus I square root of delta, which is very special value for the gapped xxz. And there you can actually put your cut one between and the other one outside. For instance, if you asymptotic case, these 2 points just degenerate at 0, so you will not have this property. Or if you study gapless case, they will live on the real line, you will also not have this state. So this is a very special state only for easy access. And I choose such that the two branch cut is between. So there's a psi1, psi2, they are in between of square root of delta. And in this case, it's a two-cut solution, so it's some elliptic function, so you can solve it by solving the problem that I showed you before, the Riemann-Hilbert problem. And then, so the P, which is the conserved charges, is some third kind elliptic integral, and you can, for instance, do the expansion, and you can check what you get. And indeed, if you want to map it back to SZ, which is actually not so trivial, because because in the sense that you only know the action variable, but you don't know the angle variable, which encodes the time evolution. You can, however, you can by solving the so-called Dubrovin equation, you can get the angle variable corresponding to the quasi-momentum, and together with this, you will get the spin field SZ. And if you plot the SZ, which is in terms of some elliptic function, it's periodic because I chose periodic boundary condition, and it has some kind of domain wall structure, if you want. So this looks like a bunch of spin up here and bunch of spin down here. Yeah, but now they are periodic, so you put them together. And in this case, it very much looks like the thing we are looking after, right? This is the thing that we are after. But this is your classical, so you might say, aha, but what happened in quantum? So in quantum, actually, we know that since in the quantum equation, in the quantum case, the solution to this Riemann-Hilbert problem, namely the asymptotic Bethe ansatz, is the same as the classical quasi-momentum. So what happened if I just solve the quantum problem with, for instance, the two ending point of my Bethe string here and here, right? So you can actually, in principle, you can actually solve this, and then you solve all the Bethe roots, leave here, and then you plot them. And you might wondering, is this the so-called domain wall state that corresponding to the frozen of the gapped xxz chain? Yeah, that would be nice if you can understand this. Yeah, but there's one slight problem, exactly as you commented. You solve the classical model, it doesn't really care where you put the branch cut. I mean, you can put it here, or you can put it here to infinity, it really doesn't matter. But however, there's some reality condition, which means if you're really solving Bethe equation, you know that once if you move along your path, your cut, you start solving some, just for example, you just start solving the Bethe equation, you know the two ending point, and then you would put the Bethe equations along some cut. And then the point is, if you move along this cut, every time you hit Bethe roots, it add 1. It's like a counting function. It's always real. It never gets imaginary. If you choose like a different path, then of course, if you integrate along here the density, it will get imaginary, or complex, let's say complex. But however, if you're really integrating along your true, let's say where the Bethe roots leave, they will give you like always a real fitting fraction, if you want. So the integral of, so you start with your branch point, and then you integrate along your physical cut, or the where Bethe roots leaves, to any point in the middle. This gives you some real number smaller than 1. So this is the condition that I choose. And then you can impose this condition to, for instance, to the two branch point that you choose, and then you realize that okay, then you will have, for instance, there are 3 basically possible solutions to it, which is explained more or less by this paper in the asymptotic case, but we're more interested in anisotropic case, but it's very similar. And then you can check what is the filling fraction, for instance. For instance, here it will give you the filling fraction which is correct, which is smaller than half. The other one give you 1 minus mu, and the other give you infinity. But these are all real, so this, in a sense, this is okay. I shouldn't put it here. Maybe I would say this integral is always real. That gives you three possible way, and really the physical Bethe roots actually only live on this one, on the short one, because they give you the right filling fraction. So I mean smaller than half, which I mean is basically if you have more than half, you can just reverse all the spins, and then you get always smaller than half because it has this symmetry. Yeah, and then this is actually some additional condition, and this is very nice because it tells us where the Bethe roots lives. And for instance, you can try to solve the Bethe equation by by increasing the size gradually, like numerically, increasing the size while keeping the ratio of the down spins with the total spin fixed. And then you will see that if you scale it with the system size, you will see that it will start to converge to this cut, rather than any others. This I would call it a physical cut because it gives me where the Bethe roots live. And this is my, let's say, the main part of my talk, which basically tells you how to go from the quantum integrable system to a classical one, and try to solve the classical one and try to get some information from the quantum, because basically what I did is I mapped the quantum Bethe equation to the asymptotic Bethe equation, which is equivalent to the Riemann-Hilbert problem for the classical integrable systems. And you can actually write down many examples, for instance, a spin wave or this baryon state that I consider. Or if you want, you can also write down a generic two-cut solution which give you some bump, look like a bump. So it looks like a soliton in the classical limit. And more importantly, you can get lots of properties. You can learn a lot of, for instance, the conserved charges you can just obtain by studying these Riemann surfaces. But then the most, let's say, interesting part, which we haven't entirely finished, is how to understand how to make use of the information that we have learned. And one of the most, let's say, interesting thing that developed recent years is actually you can, instead of calculating the overlap of the Bethe settings, instead of calculating the determinant formalism, which is in this case, in many Bethe roots case, is a bit horrible because it's infinite dimensional determinant. It's not even very easy to evaluate numerically. You can actually calculate something such as a functional integral, which of course is you guys might be very familiar. It's developed mainly by Professor Kostov and other people in UK and other places. And the idea is to see that if you know where the Bethe root lives, you can actually write down where complicated Slavnov determinant into some functional integral along some contour just along the physical cut, or where the Bethe root lives. And since I'm not the expert, so but what I want to convince you is that since I can solve the classical problem, so I know where these Bethe roots are, so I can actually evaluate, for instance, the overlap of different Bethe states. Or better here is even that this V can be off-shell, so it can be off-shell Bethe states, and then it's only in terms of the quasi-momentum which we have obtained before. So this is the object that we know. We even know the cut, so we can design the contour. Yeah, and that's kind of a very nice way of obtaining some quantum, some quantum object from just doing the classical integral basically here. Yeah, and okay, so our goal is to understand this domain wall dynamics. phenomenologically, we see that there's already some quantum classical correspondence, especially paper by Gregoire and Vincent, that they really, it's really on top of each other with the quantum simulation and the classical simulation. But however, we want to have a more quantitative way to show that. Namely, we want to calculate the overlap between the real quantum domain wall, which is not eigenstate, with the eigenstate of the bion, which I showed you before, and to show that this overlap is actually of order 1. But however, this is not true because we choose the limit where this small delta it goes to the small delta is order 1, which means big delta very close to 1, which means actually the width of the domain wall in the quantum limit is infinite, because I have a finite range of my classical domain wall. So my classical domain wall looks like this. So this has a finite range here, let's say W, and this W is proportional to basically the number of quantum spins times the lattice spacing, which basically means this is of order 1, which means this big W, which means the number of the quantum spin goes to infinity, because A goes to 0. So indeed, in this limit, you can actually, I did some numerical study of this overlap, and I realized that actually, indeed, there's some constant which is negative and is not vanishing. It's some number for the 1. But however, we know that where the true quantum model lives, so which means you can increase your small delta, and then which basically means you want, so small delta is proportional to this, and this you want to set it to of order to infinity, which means large delta goes to of order 1. Large delta minus 1 goes to of order 1, and in this limit, I also put the two rapidities in my bion state close to the point, to this special point, and in that limit, so this two determines the width. So if they're closer, this width gets smaller, and then you also increase your small delta, and what we observe is this constant start to approach 0, which means so this exponentially small, because the log term, so this exponentially small contributions start to vanish. But it's still kind of in progress, so we haven't really finished everything there, but we clearly see this behavior, which gives us a very good hint that it could work. But then, of course, you might ask what happened to, let's say, what is the order 1 overlap? And then this corresponding to the next correction to this order, because the previous equation here is proportional to the size of the proportional to the size of the spin chain. So the next order we still haven't calculated, but this will be a nice exact way to show that this classical state, right? I showed you this bion state, classical the state has classical limit, really has a, let's say, has a non-vanishing overlap with this truly quantum domain wall, which actually is not a finite temperature, and the dynamics is completely dominated by this state. So this is a kind of would be very nice to show. We are still working on it. Yeah.
Why do you choose the word bias?
Yeah. So that's because we see this behavior. So we see this domain wall-like behavior. It really looks like the domain wall that we consider. Yeah. But then, of course, when you can choose the parameter here, you have this. You make this too close to this point and make this point large. This will get sharper and sharper, of course. And of course, ideally, it will be, let's say, of like very sharp, and then this will correspond to the quantum domain wall if you want. Yes.
Could
you make something?
Yeah.
You could make different angles. It's not obligatory that you
Uh,
have
What do you mean? If you move it? Or?
no, just this kind of domain works where you.
Ah, okay, I see what you mean. Yeah, that at the moment I don't know the answer, but maybe it's interesting to study that. Yes.
You could also put several.
Ah,
Not just
so
two.
That would be far from making a state of it.
That's a question.
yeah, that's a question that we still
Because
haven't
of course
answered
it's
completely.
not the problem of starting from any initial condition and letting time evolve. It's really
Yeah, so I'm not claiming that for any initial condition it will work. This actually will not work in any initial condition. You can just imagine if you put a neo state for a ferromagnetic chain. This will definitely not work. But for this special one, which is the one that we like, goes like this, is actually has a classical correspondence. So it's not.
It's very brutal what you do on the classical spin.
Yeah.
You make a very strong on a very short distance. It's not continuous at all. Your S.
My spin field.
Point of discontinuity of the
It's not really discontinuous. Okay, if you take the limit that really goes very close to quantum, it will become discontinuous. But of course, if you relax this condition that you see that you only study this very close to the isotropic point, they are very smooth. Yeah. So again, there's a matter of limit, so you need to be a bit careful there. But yeah. Okay. Anyway, I would like to conclude. So today, what I showed is you can take a semi-classical limit of the quantum integral model, and it will become from the quantum Bethe equation, become a asymptotic Bethe equation, which actually is the same as a finite-gap integration for the classical model. But as some of the audiences have noticed, so maybe there is something deep there. So so because we start with some Hilbert space, and then in the classical case there is no Hilbert space. How to understand this? So I'm not an expert on that, but of course I would like to hear about your opinions on this, but I have no idea at the moment on that. And then the next one is basically we really want to establish some quantitative way, quantitative method to have an exact quantum classical correspondence. And more importantly, can we calculate some other interesting objects such as entanglement entropy or some other object which, because if we have the overlap, you already have knowledge to many different quantities, right? So in the quantum quantities. So can I, for instance, use this method and then try to calculate some purely quantum objects analytically from this? And this is the question that we have been thinking about. Okay, that's the end of my talk. So I would like to thank my collaborators, Sasha Gamuyun, Landau-Lifshitz, and Jean-Sébastien Coe. They are all in University of Amsterdam. But Ine will move soon to Ljubljana, so maybe some of you might know. And also I would like to thank ERC for the financial support. Thank you. Yeah.
For this variant configuration which you found,
Yeah.
you can put, it has some energy, classical energy.
Right.
Does the classical energy depends on those conditional configuration?
It does. Yeah.
But then the question is what is the minimal energy?
The minimal energy, of course, when you degenerate this. But when you degenerate this, it means the system starts going to infinity. It's kind of go to soliton limit, so it's a bit, yeah.
Namely, I'm not special from this field, but namely with respect to go for the evolution of the state, need to go to the state of minimal energy.
So okay, so I mean, of course, in the quantum case, it also has some energy, right? Because you twist. So and exactly as some numerical studies by Bourgois and Monson, they put the energy density the same, right? That's kind of. So it has some energy density, and in my case, the minimal one is when you really degenerate them, but that's exactly you would imagine to be the corresponding to this real quantum domain wall. So if you away from I mean, just for the study of a classical model, you can put it wherever you want, and then you can calculate the energy, and then you see what happened if you move the branch point, which is the only information you know for the energy. Yeah.
You cited Jiang for the
Yes.
for the overlap in the
Right.
XXG.
Yes.
So there is also another paper by Konstantin Babenko.
Okay.
Who I know that the result was obtained before, but he was slow in writing. So
Okay.
this paper appeared later. But maybe you can also.
Yeah. I don't know this paper by Babenko, but I would like. Yeah. Please. Yeah. Thank you.
So you show the Z component of the magnetization
Yeah,
for the
right.
pion
Yes.
configuration.
What
you know
happened with the other
X and
two?
Y,
Ah.
for example?
Very good question. So indeed, from the time evolution, which maybe I have some slides on that. Yeah. So from the yeah. So you can actually reconstruct it by studying the the other problem, which is called Dubrovin equation, that encodes this gamma, which you can think of it as the angle variable for the p. So p is kind of a action variable. It's not evolving with time, but this one evolves with time with some simple way. And then the point is that you can actually reconstruct SZ. It's relatively simple, but S minus is a bit more complicated. But they, as far as I remember, they are not static, but they also kind of have some kind of processive way. Yeah, exactly.
So P gamma, these are the angle action values.
Yeah, this gamma is the, you see here, you can study. Yeah, but it's some technical details. So if you want, we can discuss privately on this.
Gamma is the zero function.
Yeah.
So gamma is zero.
So if you study this Becker-Hieser function, it's the zeros. Yeah. But
Okay, sorry. Thank you
Yeah.
very much.
yeah, thank you.
Very good, thank you.
Yeah. Next one.
We can discuss.
Yeah, sure. I mean, I can also discuss it more from you first. Okay.
I have to leave and
Okay. I'll try to. Yeah.
are you going to find me or in the room?
I can show you to, I think tu vas être dans ton bureau, oui. I can show you.
Okay. Yeah. Thank you.
Okay.
Yeah. Thanks.
So I have another question. So
Okay.
what's your suppose you take the domain wall initial condition for the quantum chain, but you perturb a bit the XXZ Hamiltonian such that this is still a ground state. Well, no, this is still an eigenstate. This is still an eigenstate, but you break integrability, like you put some second neighbor interaction or whatever.
Okay.
Because all this is heavily based on